In this section, we're going to look at confidence intervals. From the central limit theorem, we know that z equals x bar minus mu divided by sigma over the square root of n, provided that the sample size is sufficiently large or the population is normal. Thus, in general, a confidence interval for the population mean can be found by using the following equation. X bar plus or minus z times the standard deviation of the sample divided by the square root of n, where z is the critical value corresponding to the desired level of confidence. The point estimate is x bar, and it is the center of the interval. The margin of error or maximum error is z times sigma over the square root of n, and the standard error is sigma divided by the square root of n. In general, we usually use 90%, 95%, or 99% as our levels of confidence. If you consider the number line, and x bar is in the center of our interval, then our lower limit is going to be a distance of z times sigma over the square root of n away from it. So here is x bar minus z times sigma over the square root of n, and to the right of it we have x bar plus z times sigma over the square root of n. So the point estimate is the center of the interval, and our margin of error is that number z times sigma over the square root of n. So I take the point estimate and I add or subtract that margin of error to get my confidence interval. So think about a basketball hoop and making that shot. The wider the confidence interval, the more confident I will be. The smaller the confidence interval, the less confident I will be. When we're constructing a confidence interval, we're using it to estimate the population mean. We don't know what the population mean is. We're constructing a confidence interval by taking a sample mean. Now, when I take the sample mean, I create my margin of error by adding and subtracting z times sigma over the square root of n. But remember, x bar is done at random. How do I know that this random sample contains the true mean? How do I know that this sample mean and this confidence interval is good enough to contain the true mean within the interval? To be honest, we really cannot tell from our confidence interval. When we construct a confidence interval, we know that most of the time our intervals will contain the true mean of the population. But sometimes we are unlucky, like these situations here in red, where we have a confidence interval that is too low, it doesn't contain the true mean, or maybe we have a confidence interval that's too high and it doesn't contain the true mean. So sometimes we do get confidence intervals that don't contain the true mean, but we know that a majority of these values will contain the true mean. If I'm doing a 99% confidence interval, I know 99% of these intervals will contain the true mean, and only 1% of the time I will be wrong. When I construct my confidence interval, I might calculate the sample mean correctly, the margin of error correctly, and construct my confidence interval correctly. However, at the very end, there is a slight possibility that my confidence interval doesn't capture the true mean. We might do everything right, but we still get the answer wrong. That's okay, because I know that 99% of the time we will be right. The above formula has sigma in it. However, it is highly unlikely that we know the population standard deviation from the mean when we don't know the population's mean, since it is difficult to know how far the values are from the mean on average if we don't know what the mean is. What? I'm trying to find the mean. I don't know the standard deviation. I can easily find the sample mean, but since we don't know the standard deviation, we can't use the formula for the confidence interval. Since I don't know the standard deviation of the population, I'm going to replace that with the standard deviation of the sample. It is hard to know the standard deviation of the population, but we can find the standard deviation of the sample pretty easily. I'm going to use S instead of sigma because it's a lot easier to calculate S, the standard deviation of the sample. But recall, Z is not equal to x bar minus mu divided by S over the square root of n. It is equal to x bar minus mu over sigma divided by the square root of n. There's a sigma here, so we cannot just replace this sigma in here and set it equal to z. That's not going to happen. Instead, we'll create a new distribution called the student's t distribution. We have x bar minus mu divided by s over the square root of n. And this t distribution is very similar to the z distribution. It is very, very close. And if n is really large, the approximation of t is very close, extremely close to that of z. Let's look at the student's t distribution. It is continuous like z. It is bell-shaped and symmetrical like z. We have more area in the tails of the distribution than z. This reflects the greater variability that is expected with a small sample. 4. The t distribution changes shape according to their degrees of freedom. The degrees of freedom is given by df equals the sample size minus 1. 5. As the sample size increases, the t distribution approaches the z distribution. In blue, we have the z distribution, and when the sample size is 5, we can see that the t distribution is very similar to that of the z distribution. T is very similar to that of z. As our sample size increases, it gets even closer to that of z. In fact, if you have a sample size that gets really large, in the thousands, this t distribution gets very close to z. In fact, for very, very large sample sizes and greater than 1,000, we can use z instead of t because they're so close to each other anyway. Thus, our new formula for the confidence interval for the mean is x bar plus or minus t sub n minus 1 times s over the square root of n. This n minus 1 here is going to be our degrees of freedom. And notice here we're using the sample standard deviation instead of sigma. If the degrees of freedom, which is n minus 1, is greater than 1,000, we're going to use the formula that contains z because our approximation is so close to z, we'll just use z. If the degrees of freedom is less or equal to 1,000, we'll use the t distribution. Note, if the sample size is less than 30, we first have to check for normality using box plots and probability plots. If it meets the conditions, then we can use x bar plus or minus t sub n minus 1 times s over the square root of n. Otherwise, we would have to use techniques not discussed in this course.